Okay, I'll introduce the next speaker, me. I wanted to point out we've got a couple of sponsors for this meeting, folks from NEI and Hagen Trammell, and they are here in the building. All I ask is that you buy one GPS receiver from each one of them, and that will be fine. Randy, which one is it? Yeah. Actually, I'm a professional, so I can probably take any of the slides here and give a talk about them. I don't know what they mean, but there we go. Okay, I'm going to talk a bit about subsidence. Try to explain what this phenomenon is, so you can get an idea of why it's so difficult to maintain vertical control. What do engineers and surveyors need to know? We have an engineer here. I have to talk about it. Basically, subsidence moves benchmarks away from the datum. Datums are constructs. They're mathematical constructs. They're just they're invisible. The day that the datum is created is the day that these control points, these physical points that we call benchmarks, are coextensive with those points. With time, those physical things that we use move away from them. The datum hasn't changed. It's just those physical marks that we made the datum with have changed. And so the hard part is, where's the datum? I see the mark, but where's the datum? And so the difficulty is that to access the National Spatial Reference System, in other words, all of these things that help us understand where, how high things are, we need to be able to understand what's happening. And so if you're doing flood certificates and the benchmark's wrong, flood certificate's not much use. I hate to say this, but the new 100-year protection they have here in New Orleans is really not 100%. Is not going to be 100. Is not 100-year because there are a number of issues that vertical control was not totally considered. So the storm surge models that they use to figure out what your base flood elevation is was done with data that was not correct. And so it's always the surveyor and the engineer that basically has to deal with this stuff and try to do the best that you can. One of the most important things to remember about subsidence is that it's not constant. It can vary in time and space. Problem is, a lot of the ideas that go into the engineering of all of these things assumes a constant subsidence, and it's not true. The other thing is that it changes the relationship between terrestrial and water datums. You need, those of you who work on the coast, you need to know where's that water datum, where is it with respect to those terrestrial datums. The other thing is, if you're a surveyor, state water bottom law basically says if if land goes underwater, it goes back to the state, along with all the mineral rights. Let me tell you, there's more oil out in coastal Louisiana and Texas than people will let on. So this becomes very important to landowners. And the problem is, if you don't fully consider this dynamic nature of this coast, you will not be able to engineer it in a way that will make it safe. New Orleans is flooded 6 times in the 20th century, and things are still happening. So frequently asked questions, what is subsidence? Well, subsidence is not, it is a condition. It is not a process. It is a condition. It is. Okay, and it basically is the downward motion of the Earth's surface with respect to a datum, like NAVD 88 or sea level, or something. You got to measure. It's got to be a measurement related to something else. Basically, people have misunderstood subsidence because they weren't able to measure it. You got to be able to measure things to understand these processes that are happening. And it's come up, and also people have been operating under a bunch of false assumptions. They have assumed that subsidence is just something that affects the soils, let's say in New Orleans. It's not true. There's more going on. But you got to be able to measure it. And that's the key. And finally, subsidence is caused by numerous processes that all can be operating in a single place. This area right here is subsiding. It's subsiding because of this area of UNO is built on a bunch of fill, dredge material back in the early part of the century. Well, that fill continues to subside. Those coastal restoration projects that you were looking at, those were essentially, they weren't fully compacted and the soil sunk and the benchmark sticks out of the ground. But it's also a big thing that's happening right here. There's a couple of huge water wells right down the street here. And the biggest single cause of subsidence in the Gulf Coast is groundwater pumping. And they figured that out here in New Orleans back in the 40s and 50s. And here in New Orleans, we're really smart. We drink out of the river. And they clean it first, of course. But the bottom line is that groundwater pumping is a major effect. It's still affecting parts of New Orleans. There's a bridge. Anybody, you heard of the Green Bridge? That Green Bridge has sunk 3.5 feet in the last 50 years. Interstate bridges aren't supposed to subside 3.5 feet, right? You bet. Where does it happen? Well, the fact is it affects everything along the central Gulf Coast from probably about Pensacola throughout the entire coast of South Texas as well. Subsidence is four-dimensional. In other words, it's not just a map. It's also the fact that it affects areas down in the earth by different amounts, and it also varies through time. How fast does it occur? Well, millimeters per year to several decimeters per year. Very high subsidence rates in Louisiana and Texas have been, those are mainly due to things like groundwater pumping. You don't really get, on average in the coast, if you don't consider groundwater pumping, it's probably on the order of maybe somewhat less than a centimeter per year due to various processes. But you get into areas of groundwater pumping, you can get very, very high rates, 4 or 5 centimeters per year. There we go. Help. There we go. Okay. Let me go back. Okay. Well, as Tim was talking about, it's not just along the coast, it's not just subsidence, but also there's this thing called sea level rise. Well, sea level rise this is what we measure at tide gauges. And here are some various situations. This is the long term. This is over the last 20,000 years. The last ice age ended about in here. Actually, the glacial maximum was around 18,000 years ago. And all the ice melts. The atmosphere warms up. The sea level goes up. Well, most of the sea level rise really started to slow down back around 6,000 to 7,000 years ago. That's when coastal Louisiana begins to form. As the sediments in the Mississippi River basically pile up along the coast and builds the delta. And it's been very slow since this period of time, although some people think that it's going to shoot straight up here pretty soon. These are These are based on various kinds of scientific theories and observations. The globe is warming, I will tell you that. Now the question is, what's going to happen? I think this is very difficult for scientists to kind of predict. It's hard enough to figure out what happened, let alone trying to figure out what's going to happen. Over the last century, subsidence has looked, or excuse me, sea level rise has looked something like this, just sea level rise. In Louisiana with subsidence, then you have to add that to that, and that's the effect. That's why we have Grand Isle subsiding at 9 millimeters, 10 millimeters per year. It's not just sea level rise, it's also the land sinking. So the combined aspects of it. But you see, it hasn't been rising all of that much. It's about 2 millimeters per year. Some people will tell you, based on radar altimetry, that maybe it's up to 3 millimeters in the last 20 years. The jury is still out on that. Here in the Gulf of Mexico, these are tide gauges. Here's Pensacola, 2 millimeters per year. In other words, there's not a lot of subsidence going on in Pensacola. On the other hand, Grand Isle shows a lot more. This is the most recent, or this is the old tide gauge, and then the new tide gauge is up in here. And it's about 9 millimeters per year. So you subtract Pensacola out from this and you get about 7 millimeters a year of subsidence at Grand Isle. Eugene Island down in Vermilion Bay, same kind of thing, high subsidence. We could look at everything along the coast, we'd see that there is some aspect of some sort of sea level rise that is not fully explained by just global sea level rise. Okay, a couple years ago, Kurt Schinkel and I analyzed all of the first order geodetic data that NGS had in this region and came up with this. This is the subsidence of benchmarks. It's in Technical Report 50. It makes great insomnia reading if you can't sleep. But the important thing is that it shows that subsidence rates all along the coast of Louisiana are extremely high. We get up into Alabama, you actually have areas of uplift in the Appalachian Mountains. You see that subsidence gradually increases as you get towards Louisiana. We see that there's subsidence in other areas, hot spots of subsidence that occur in various places, and you begin to wonder what's causing it. People will tell you that it's all just due to subsidence in the coast. Some people will tell you there's no subsidence at all. And, but again, it comes down to measurement. And we can see that along the coast here, back in the 60s and 80s, on average, subsidence was going on at about 1/2 an inch per year. As Tim indicated, that the low elevations of this area, that's not a good thing. And of course, if sea level suddenly, if Al Gore's right and suddenly it goes through the roof, then we're going to be in some real trouble. It just doesn't happen in Louisiana. This is in southeast Texas. This is some historical data where we've analyzed the data over in Texas, and you see the rates have been extremely high at various times. This is from Galveston up to Houston over to Beaumont and to hook up with the stuff that we did before. And you can see over time there's been a lot of subsidence in this area. Okay, most of this stuff is due to groundwater pumping, and I think people in Texas have done a good job trying to understand that and trying to curtail that. The problem is goes a bit beyond just that. It gets to issues of how has that subsidence affected the vertical control, and how have we done anything to alert people to these problems? What causes subsidence? Well, I divide subsidence into two things. One, shallow subsidence. That's a subsidence that occurs due to processes occurring above the main producing aquifers in an area. Around here, the big aquifers at about 700 feet. And that would include natural compaction, human-induced consolidation and compaction. This is due to when you build levees. Building levees is a bad thing in terms of subsidence. On the other hand, you have to be insane to live in coastal Louisiana without a levee in front of you. Imagine tearing down the levees here in New Orleans. It's below sea level. Well, it wasn't below sea level when people moved here. It's a strange thing. People in the rest of the country think that we move. What do we call areas below sea level here in South Louisiana that are not protected by levees? What do we call those things? Lakes, correct. Okay? And so when you build a levee, you're going to get subsidence. It happens at about a foot per decade, roughly. There's also, we have all of these very organic soils. Well, you start doing forced drainage and pumping the water out, you replace that with air, and that eats up all of the organic soils, these mucks that we all have to worry about. That's an engineering word. What about deep processes? These are below and including the aquifers. Well, there's one of the major things is the fact that the Mississippi River Delta is a big pile of goo that sits on the crust, depressing it. There is a load. You can do these calculations just like you would do for a bridge or a beam. And as it turns out, you can get up to about 8 millimeters per year centered on Cocodrie, Louisiana, the areas that show the most effects of subsidence these days. Faulting. There's faulting that goes on around here. Salt evacuation. There's salt domes. So salt domes are moving around. As they move around, causes subsidence to occur. Water pumping. Oil and gas extraction. This is something that people have really gotten excited about. I guess it's because oil companies have a lot of money, and so we can sue oil companies. But as it turns out, there's really, when you look at the science, you really can't explain a lot of the subsidence by oil and gas extraction. However, you can, water pumping, huge factor. The second, that and building levees are the two major causes of subsidence. Followed by the other thing that happens is the sediment loading. Those are the three big factors causing it. Well, this is just a little cutesy diagram showing forest drainage causing you essentially de-water the upper surface soils. You notice the canals in New Orleans, they're always filled with water. Why? Well, they figured out a long time ago is when you pump them down, it drains the surface soils and it compacts. And they don't want that to occur. So what does shallow subsidence look like? This is a nice house out in, this could be anywhere in New Orleans. This is in New Orleans East, and you see that inviting home there with a big, broad driveway. Is that a driveway? Or excuse me, walkway. But it ends suddenly in what appears to be, and you see this in Houston, you see this everywhere, where basically people convert their garages into, because they can't get in there anymore. Okay? See the little ski jump here? I know this is not engineering, bad engineering. This is just, the house, this house is built on piles that go down into the earth, maybe in this area, maybe 30, 40 feet. It goes through all of the compacting soils, and the street wasn't though, and the driveway wasn't, so it sinks, but the house stays up. Then they have to, it kind of gets unsightly, it gets on the honeydew list of whoever lives here, and that's what it looks like. Or it looks something like this, where it's just totally collapsed. And so you see the effect here. The effect here can be amazing on the infrastructure, sewers, water lines. There was a time after Katrina that there was something like, in fact, it's probably similar today, that there's 20, 30, 40% of the water in New Orleans in the water pipes are leaking. Well, you see this kind of subsidence, differential subsidence could break a lot of those lines. Here is one of the subsidence, one of the benchmarks poking out of the ground. Well, you know, they've got these yellow posts around there because to keep the lawnmowers away. Lawnmowers run into these things. When they do that, benchmark 1, lawnmower 0, right? Well, what's happening here is that it's very simple. It's that shallow subsidence. Here's the benchmark. It's when they put those things in, they're maybe 6 inches below the surface. They sit there, and the ground compacts, and it sticks out of the ground. Lawn mowing guys along Chef Menteur Highway back in the 90s, according to Cliff Mounier, were outfitted with hacksaws. That's another place where all of our control goes. And you can see this is basically the idea. Here's the benchmark set below the ground surface. Over time, this is a deep rod mark pounded to refusal. Well, it's that surface soil then that compacts, resulting in the thing sticking out of the ground. But that's not everything there is to know about subsidence. There's something called deep subsidence. Well, conventional wisdom says it's just shallow because it's, you know, you see it. Well, you got to measure it. You just can't see it. You got to measure it. And it's always people have thought it was constant in time and space. It's really not. Geodetic data, when you analyze it as a function of depth, shows that it's variable in time and space. Plus, it also affects the horizontal as well. Even our GPS stations go up and down every year just from the fact that the groundwater is pumped, recharged, and goes up and down. These are another one of the potential pitfalls, as Dave was talking about, that we have to be concerned with. So in order to measure subsidence, you really have to understand the processes that are causing it so you can develop a measurement strategy. That's where I come in as a geologist. I kind of understand some of these things. What we can do is now use the technologies of surveying to help us see what those things are, and the combination of the two is pretty good. So in the end, a lot of geodesy is all about the monumentation. Surface mark, deep rod mark, you see differences when you look at them. As you can see here, here's the Paris Road Bridge. You know that bridge is on pilings that go down at least 130, 140 feet. Surface soils in New Orleans East are very shallow. Maybe, I mean, they're not very thick. Maybe they're 20, 30 feet thick. Well, we know this stuff goes through, those pilings go through there. Houses there as well do the same thing. This is standard business or standard practice in much of New Orleans today. But you can see that you will measure a different amount of subsidence if you have a surface mark as opposed to a mark sitting on a piling or a bridge or a radar reflector sitting on a house that's built on pilings. They will see different amounts of subsidence. All right. So the main processes to kind of review again are these. Well, here is this deep subsidence that I was talking about due to the load of the Mississippi River Delta. These are some models that we constructed using standard engineering techniques to see how much deflection of the Earth's crust there was. The Earth is not infinitely strong. It behaves just like a beam or a sheet. And if we put a load on it, we can measure we can get an idea of what we might expect. Freshwater bayou subsides at about 3 millimeters per year. Our model, it's pretty close. And so this gives us confidence that this is correct. The Wrigley's, over the old Wrigley's Bridge, J92. J92 turns out to be subsiding back in the 50s, 60s, 70s, 80s in a very constant way, incidentally, due to this process, because this process is very constant. It's not going to stop anytime soon. And so that confirms it over here. Same thing with Cocodrie, same thing with Grand Isle. So we get confidence that this process is operating. We do exciting things at LSU. We're going to turn them all around. There we go. Okay, when you look at level lines and look at subsidence rates from Pensacola all the way over to Grand Isle, you see a pattern that looks like this. If this was just this tectonic loading business, what we would see is something very continuous. But we don't see that. We see these deflections. This is New Orleans East. We see some areas, interestingly enough, some areas may be going up around here. Here's the thickness. I want to point out that these little crosses here are the locations of water gauges. These water gauges these are Corps of Engineers water gauges. Robert Frost in the audience worked this stuff up for the Corps back in 2008, I believe. And we've used the same data to try to examine whether Schinkel and Dokka were actually correct. We're looking for corroborating data. As it turns out, it works out very well. All of those gauges are on deep-set bridges or locks or things like that. Well, when we look at subsidence across this area, we see, this is from Biloxi over to New Orleans, we see very small amounts of subsidence in this area along the Mississippi coast, which you might expect. But as you get into, suddenly you get into New Orleans East, subsidence just goes crazy. And we see this is since 1969, and this is since 1969, yes. So this is, after you take out the amount of tectonic subsidence, this is what we're left over with, and I suspect most of this is due to groundwater withdrawal over in New Orleans East and in this area right here. Here are the water gauges. They show the same story. Huge amounts of subsidence back in the 60s. This is using water gauges. You subtract out the sea level rise, and what's left over is the subsidence. And here's the Wrigley's, nice and regular, but then you see these exponential curves. This is the Green Bridge over here, or the Parish Road Bridge, whatever you want to call it. And these other guys are other bridges in the New Orleans area. And we see that the Green Bridge here shows enormous amounts of subsidence. In fact, if we look at these other gauges and take them out to the present, they basically have stopped subsiding, which is interesting. That's because probably the economic development, they're not pumping as much water in this region because there's not a lot of industry left. Well, here's the Green Bridge. This is over from Chalmette, is over here, over towards New Orleans East over here. These are the subsidence, the amount of vertical displacement of benchmarks along this traverse in here. Here's the bridge, inset over here. What this is showing, I think this looks like what you'd expect to find around, this is a cone of depression, as they call it. Right in here, right at the foot of the bridge, is the Entergy power plant. And there are some very large wells over here that have been pumping like mad for the last 50 years. And this has caused a drawdown of this area along with subsidence pulling the bridge down as well. The problem is, if you know this area right over in here, this is where that big plug is. Or I guess the plug is over here, isn't it? That's supposed to protect New Orleans from flooding from the east. Well, I'm sure they haven't used this data in their projections of how long the design will hopefully last over here. So the bottom line is Louisiana's coast, we talk about the wetlands, but it affects everything, not just the wetlands, but also where people live. We know that the river was built, the delta was built by sediments being piled up here, but it was balanced, the equal sign, it was balanced by global sea level rise, oceanographic effects, and subsidence. Well, we know today there is no accretion because we've dammed up the river. It can't flood. Of course, we can't live here if it floods. So this was the pact with the devil that we made. Now today, the only thing that's happening is subsidence plus sea level rise, which is leading to the slow deterioration of marshes as they die away, saltwater intrusion, and all of those things, plus increased vulnerability due to hurricanes. So let's predict the future very quickly. You've all had enough time to digest your food, so this won't be too messy. What we're going to do is to try to look, we're going to use the recent past to look at the future, only including those things we're pretty certain are going to continue. We're not going to include water pumping because I don't know if people are going to stop pumping after they see all of this. But we can talk about some of the things that we know that are going to happen, like building levees, and that's going to continue. The tectonic subsidence is also going to continue. So here is the existing hurricane protection systems. Again, here is, here's Morgan City over here. Here's Morganza, the Gulf. Homa's over here. New Orleans is over here. If I'm living in Homa, and I will tell you this, build a levee. You don't have a prayer. If a hurricane comes in the right orientation, it will flood Homa. You need to have this. Or you need to get honest and tell people to move. But you can't protect yourself just like New Orleans has. If you do it right, it can work for a while. So these are the areas that are going to be affected by levee building. And what people need to understand is that here is what it looks like today. In magenta are areas that are at or below sea level. 2050, it's going to look like that. There's going to be a bowl forming in Homa. There's already a bowl. Everybody knows that there's a bowl in Morgan City. It's below sea level behind the levees. Every levee, you go to Port Arthur, Texas, it's below sea level, inside the levees. However, you can't live there without a levee. And this is what it's going to look like in 2100. Well, here is some of you close can see this. This is the percent land below sea level by parish through 2010. In Orleans Parish, everybody knows that half of Orleans Parish is below sea level. It's going to be 85% at the end of the century. I've decided I will not be here. I'm not going to see this. Jefferson Parish, 34%, it's going to be 68%. Plaquemines Parish, a quarter of it's below sea level right now. It's going to be, 62%. Of course, it depends on how much Billy Dungesser eats in the next couple of years. Ooh. St. Bernard, half of it's going to be below sea level. But the point is increased vulnerability to hurricanes and flooding, because that's not going to stop. So that means they got to keep up the height of the levees to the design. As those areas subside, we got to build them up again. And that's where you guys are absolutely essential, because you're the ones that are going to tell people how high everything is. So, in conclusion, subsidence has and continues to it's a challenge for us in maintaining vertical control along the Gulf Coast. Anthropogenic, fancy word for man-induced, is the biggest single driver of subsidence. It always has been. It's going to be that way. We can make choices about this, but the natural things we can't, and those are going to continue. And groundwater pumping and forced drainage dominate the subsidence, and the loss of elevation is effectively making it more vulnerable to hurricanes into the future. People need to understand that. You are the folks to tell society, not me. So, thank you very much, and we're going to wait on questions that are until later. Our next speaker is Renee Shields, and she's going to tell you about the resources of the National Spatial Reference System here in Louisiana.